Hi, in this presentation we will look at the specification proposed for the third and last part of our compulsive coursework plan, which in this case addresses the implementation of a boundary scan test controller. After watching this presentation, I hope that you will be able to explain this specification in your own words, and also to identify the main design tasks and to set up a plan for your development work. Your boundary scan controller must support the functional requirements summarized in this slide. There must be one test access port or TAP, comprising the four usual test beams called test data output, test mode select, test clock, and test data input. If the board has multiple boundary scan chains, then we will need multiple boundary scan controllers present, and that is why we need this simple handshaking mechanism. And finally, the overall objective is to run a test program stored in a local ROM, comprising a set of test instructions that will be presented in a later slide. This is an overview of a board comprising two boundary scan chains and the corresponding boundary scan controllers with their test programs stored in local ROM. Notice the names used because they will be referred again in later slides. The word master or letter M preceding the pin name indicates the boundary scan controller side. For example, the MTDI pin receives the bit stream coming out of the TDO pin of the last device on its boundary scan chain. What you are being asked to develop in this assignment is only the boundary scan test controller that is represented here. And here's a block diagram of what your boundary scan controller may look like. You may, of course, adopt a different architecture, provided that you comply with these specifications that are presented here. This actually represents a typical von Neumann processor architecture designed to execute a set of instructions stored in the program memory. In this type of processors, you will need an instruction register to hold the opcode or operation code of the instruction to be executed, which is fetched from memory using a data bus and an address bus. The brain of this architecture is the instruction register and its instruction decoder and execution control unit, which issues the orders to the remaining blocks, such as the counter to generate the ROM addresses. This block is normally called program counter and controls the address bus. And of course the specific registers that are needed by our instruction set. In this case we will need a modulus counter to count the required number of test clock cycles, and two serial registers to handle the serialization and deserialization tasks for the scan path. And finally, a latch to handle the synchronism and error detection outputs. You may pause the video at this point to make sure that you understand the reason why each block is present. And by the way, is this a finite state machine with a data path architecture? Where are the control and data paths if that is the case? And here's a list of the instructions to be supported with their opcodes on the right. TMS and reset are very simple instructions that are used to control the state transitions in the tap controller state diagram. NTCK, as the name indicates, generates NTCK clock cycles while holding the MTMS pin at 0. The two most important instructions are shift and compare, which scan test data in and out of the scan path. Shift scans a bit stream out of the MTDO pin, but in this case it disregards the bits that are received at the MTDI input. Shift and compare also scans a bit stream out, but in this case the test responses received at the MTDI pin are analyzed and compared with their expected values. Because we may not know what to expect in many bit positions, we need a mask to indicate which bit positions are to be compared. When there is a difference between a bit received at MTDI and its expected value, and if the corresponding mask bit position contains a logic 1, then the error detection output must be asserted. The rest of the instructions deal with the synchronism inputs and outputs, and halt is used to stop the test program at the end. Now, shift and compare requires an additional explanation. Notice that this instruction comprises 4 arguments, the first of which is the number of bits to be scanned. Then we have 3 bit streams comprising the bits to be shifted out through MTDO, the bits expected at MTDI, and their respective masks. We might interleave these bit streams in the memory, or we might pack them into a series of consecutive bytes. I have chosen this second option here, where you see the shift and compare, that the shift and compare instruction is stored in program memory, starting with the opcode. Then the second position contains the number of bits to be shifted. And then we have a variable number of bytes storing the bit stream to be shifted out, then an equal number of bytes storing the expected responses, and finally the same for the mask bits. Now, I have used different colors here to distinguish between these bit streams, but I suggest that you pause this video now and look carefully at this example that I have prepared for you, which corresponds to the specific case of shift and compare instruction handling 15 bits. So, what do I mean by designing an instruction? Let's consider the case of NTCK. I had to use a smaller font here, but you have access to these slides where you can read this easily. You have to specify exactly what happens in the boundary scan controller data path while each instruction is being executed. You can do this by drawing an ASMD chart for each instruction and then combine all the charts into the overall ASMD chart of the boundary scan controller. Let's look at the case of NTCK. We have to start by loading the instruction register and incrementing the program counter so that it points to the next byte. Then we need to check if this is the NTCK opcode. Notice that these 2 initial states are common to all instructions, and that is why I call them all 0 and all 1 for these 2 states. Then we must check if n is equal to 0, and if not, then we can start by alternating between these 2 states, where TMS is kept at 0 and MTCK toggles as many times as indicated in the second byte. In this case, it is 17 times. Again, you may pause the video at this point and look carefully to make sure that you understand every detail. So, what are you being given and what are you being asked? You are given a ROM description in a file called ROM_unit, or in a file called rom.vhd, which contains the test program to be executed. This ROM has an 8-bit data bus and an 8-bit address bus, and it has no control signals, so there are no read or enable signals. You are asked to develop the boundary scan controller that goes into this position here, the boundary scan controller unit, and of course the top level description as well as shown here. Please support all these inputs and outputs. They are used in the test bench file that is also given to you. Before closing, I'd like to show you the simulation of my own implementation using the ROM and the test bench files that are given to you. This test program contains a mix of instructions that you are asked to support, so it was not created to represent a real test program. This slide shows the sequence of instructions, their storage in ROM, and the waveforms at the boundary scan controller tab. I have modified the original test bench in order to simulate an unexpected response at the very last TCK cycle of the shift and compare instruction. As you can see, the error detection output goes high at this point, and then it remains at 1 for the rest of the time. Again, pause the video here and make sure that you understand the relationship between the ROM content and the waveforms. These two slides show you the same waveforms but in larger size, and I point out some important details that you have to take into account. In this case is the reset, TMS, shift and NTCK instructions, and in the second slide is the shift and compare SSO, WSI and halt instructions. As in previous assignments, I propose you a roadmap that alternates between group work and work on your own. And please take into account that your deliverables are due by Sunday, November 27th, and this is a more complex assignment. For that reason, it also extends for a longer period. You have 3 weeks instead of 2. And recall that your deliverables must comprise a presentation and the Vivado project folder. And that's it. You are now ready to start your final coursework assignment. I wish you a good work.